All right, so in this video, we're going to be introducing a new term called the degree of unsaturation. The degree of unsaturation is going to be a mathematical calculation that we're going to do. And it's going to give us a whole number that's 0, 1, 2, 3, 4. And it's going to describe if there are specific features in our molecule that's going to be really helpful for us drawing structures. If we just give you a molecular formula, as we kind of like have like some examples down here, like if I just give you C6H10NBr, and I ask you to go through and draw that in terms of a skeletal structure, that's a little bit more challenging because there's a lot of different things you need to figure out, and typically you'll kind of like start that in terms of like a Lewis structure. The degree of unsaturation is going to be a quick math that we're going to do that's really just going to be like subtracting and dividing. So it's pretty straightforward math too. That's going to tell us if we have double bonds, if we have rings, or if we have triple bonds in our molecule. Now, these terms of saturation and unsaturation, you might have randomly heard of before when you think of like saturated fats or fatty acids or unsaturated fats and fatty acids. And that idea of being like fully saturated really means, do you have the maximum number of hydrogens that are possible? Generally, things that are fully saturated are a lot more stable and less reactive, where unsaturations are like spots where you can like do chemistry a little bit more likely. So let's go and just consider a 2-carbon system. So if I have just a carbon bonded to a carbon, how many total hydrogens can I stick onto those carbons? We know that carbon wants to have a total of 8 valence electrons, and to do that, it typically will have 4 bonds. So I can put a hydrogen here, a hydrogen here, hydrogen here, hydrogen here, hydrogen here, and a hydrogen here. So I can put a total of 6 H's onto my 2-carbon system, and this would be an example of a fully saturated. So that maximum number of hydrogens would be 6. Now, if we consider something that's super similar, so a 2-carbon system, but here we have a double bond. Let's do that exact same math and calculate how many hydrogens we're able to stick on. Now, we know that carbon wants to have a total of 4 bonds. 2 of them are already taken, so I can put 1 here, and 1 here, 1 here, and 1 there. And this would give us a total of 4 hydrogens. This is an example of something that is going to be considered unsaturated because it does not have the maximum amount of hydrogens. It's short. There are 2 more hydrogens that can be added to it. And one thing that we'll actually learn way at the end of this semester, one of our final units, are actually like chemistries on like double bonds. And then in Orgo 2, you'll talk about chemistry of triple bonds and ways to actually add things to those double and triple bonds. So anytime we have a double bond, a triple bond, or a ring, there's going to be a shortage of the amount of hydrogens that you can add. And that's going to be the thing that we're actually going to be calculating. So the math part of the degree of unsaturation is we're going to find out what is the maximum number of hydrogens we can put on our normal system. And then we're going to subtract out how many hydrogens there actually are and then divide that by 2. And the reason we divide by 2 is anytime you get a double bond or a triple bond or a ring, it's going to be associated with 2 hydrogens. So we're going to divide by 2 just so we're not double counting stuff. Now, to figure out how many hydrogens you can put on a carbon system, there's going to be this kind of formula 2n plus 2. And 2n plus 2 is going to describe the maximum number of hydrogens you can put on a n-carbon system. So if you have, for example, 2 times 2 gives you 4, 4 plus 2 gives you 6. So for our 2-carbon system that we kind of proved just a second ago, you'd be able to put 6 hydrogens. As you go on and on and on, the reason you're doing it by 2 is because you'll have a methylene that's a CH2 that's in the middle, and then way at the ends, you'll have 2 terminal ones, which will be the plus 2 part. So let's go ahead and follow this kind of same mathematical formula for a generic system. Let's think of C5H10. For the C5 and H10, rather than doing this all in one, I'll generally do it in like 2 sets of math just so I don't get confused. We're going to calculate our max number of H's and our actual number of H's. So our max number of H's is going to be our 2n plus 2. So our n number is going to be the number of carbons. So here we have C5H10. That's 5 carbons. So we're going to do 2 times 5 plus 2. That's our 2n plus 2. In terms of this math here, 5 times 2 gives us 10. 10 plus 2 is going to give us 12. So in this system, we can fit a maximum of 12 hydrogens. Now we need to know how many are actually there. This part I actually really like because it's super easy. Just look at how much are written. So here we see that there are 10 that are written in our molecular formula. So there are 10. Now to do our degree of unsaturation, we are going to do 12 minus 10 divided by 2. The most common mistake outside of just subtraction is students forgetting to do the divide by 2. 12 minus 2 gives us 2. 2 divided by 2 gives us 1. And this means that there is 1 degree of unsaturation that exists in this C5H10 molecule, meaning there is a single double bond or a single ring. And the difference between those different structures, and we could draw a bunch of different ones, these would all be constitutional isomers. So if we want to draw a skeletal structure, that's 1, 2, 3, 4, 5. I could have a double bond there, could have a double bond there, could have a ring. All of these right here are all examples of potential structures that we could have for our C5H10. And there's even more than that, but those are just kind of like some super quick ones. Each of these carrying a single degree of unsaturation. Do note, I can't have a triple bond. A triple bond is the same as like 2 double bonds. So a triple bond has a degree of unsaturation of 2. So I can't have any triple bonds here. And once we calculate what that degree of unsaturation is, it's really easy to go through and actually get our structures. Our entire class is going to focus on the actual process of drawing these and thinking about strategies. So don't stress out too much about those just yet. Now, this works really well for hydrocarbons. Hydrocarbons are going to be molecules that only have carbons and hydrogens, and that's all. C5H10 is a perfect example of that. However, we know that there's going to be a lot of examples of molecules that are going to have other stuff. They're going to have oxygens and carbons, or they already have carbons, nitrogens and bromines and a bunch of weird stuff. So we do need a handful of extra rules to be able to account for all the other stuff. And there's going to be 3 main types that we're going to focus on. These are going to be halogens, oxygens, and nitrogens. And then everything below them on the periodic table matches as well. So oxygen is going to be the same as sulfur, because sulfur is right below oxygen. So let's go and walk through these 3 extra additions that we'll take into account when we have our halogens, our oxygens, and our nitrogens. Halogens are going to be our group 17 on the periodic table. So our halogens are going to be our fluorines, our chlorines, our bromines, and our iodines. Anytime you see a halogen, they are going to be very similar to our hydrogen. Halogens want just a single bond. They're super close to getting that noble gas configuration, so they only want 1 bond. And because of that, they're going to behave a lot like a hydrogen, because hydrogens only want 1 bond. So anytime you have a halogen, you're going to treat them the exact same as a hydrogen. It also kind of helps that halogen starts with an H, hydrogen starts with an H, so they're also kind of similar there. So how do you treat them like a hydrogen? What you do is you take your number for your actual H's, and then you simply add 1 to it. So in this case where we see above, if it was like C5H10 Br2, you would take your number of actual hydrogens, which would be 10, plus you would then add 1 for every single halogen. Here you'd have Br2, so you would add 2, 1 for each of the bromines. And we'll get a ton of practice with these in class. I just want to kind of get over the kind of base rules here. Next is going to be oxygen. Oxygen is my favorite because oxygen wants to form 2 bonds, and that means it doesn't affect the calculations at all. So anytime you get an oxygen, you just ignore it, which is really nice and easy. The last one is going to be our nitrogens. Nitrogens are going to be trivalent, meaning they want to form 3 bonds and have 1 lone pairs. So compared to like a carbon, they can actually accommodate an extra hydrogen. So anytime you have a nitrogen, what you'll do is you'll take the number of max hydrogens that you have and then add 1 for every single nitrogen that you have. So in general, if you have oxygens, you're going to ignore. If you have halogens, you're going to add 1 for every halogen in your actuals. And then if you have a nitrogen, you're going to add 1 to your max. So let's do just a touch of math to figure out how this would be set up for this specific example here. Here we have C6H10NBr. So much like last time, let's calculate our maximum number of hydrogens and our actual number of hydrogens. So our max number of hydrogens is going to follow our same 2n plus 2 rule. So I'll go and write that out just so we remember, 2n plus 2. N is going to be the number of carbons. So here we have a total of 6 carbons. So we're going to do 2 times 6 plus 2. 6 times 2 is going to give us 12. 12 plus 2 is going to give us 14. So a 6 carbon system will be able to accommodate 14 hydrogens. And that takes care of our C6 part. Next, let's go through our actual number of hydrogens. There are 10 because it says there are 10. So that's nice and easy. That would be what we'd do for our normal hydrocarbon. However, we do have a nitrogen and we do have a bromine that we have to take into account. So these are where these extra 3 rules that come into account. We have no oxygen, so we're going to ignore. Let's go and do our nitrogen first. So our nitrogen, we're going to add 1 to our max for every single nitrogen. So we have exactly 1 nitrogen here. So we're going to add 1 to our max. And this plus 1 is going to be from our nitrogen, meaning we can actually hold 15 instead of 14 because of that nitrogen. And therefore, we've accounted for it. And then finally, our actual number of hydrogens is also going to need to be adjusted because we have our bromine. Our bromine is a halogen. Halogens are a lot like hydrogens. So we have a bromine. So we'll add 1 here to get 11. So this plus 1 here is from our bromine. And this plus 1 here is from our nitrogen. So anytime you have your oxygens, your nitrogens, your bromine, chlorine, fluorine, iodines, there'll be just a small, tiny little adjustment to either your max or your actuals based on that. Your DU, degree of unsaturation, is going to be the same though. It's going to be the max number, which is 15, minus your actual number, which is 11, divided by 2. 15 minus 11 gives us 4. 4 divided by 2 gives us 2. So this molecule, C6H10NBr, has a degree of unsaturation of 2, meaning there are going to be 2 spots where we're going to have a shortage of hydrogens. That could mean we have 2 double bonds. It could also mean we have 2 rings. It could mean that we have 1 double bond and 1 ring. It could also mean that we have a triple bond. A triple bond counts as 2, where double bonds and rings counts as 1. So that gives us a bunch of different combinations of stuff that we could potentially have in this molecule. And that's going to be the kind of main focus of our video here, just being able to go through and do that calculation. Once you do that calculation, what we're going to focus on in class is going through and actually physically drawing these to get to a actual skeletal structure. If you have a degree of unsaturation of 0, that means there is no double bonds, triple bonds, or rings. If you get a degree of unsaturation that is a fraction, so like 1/2 or a 0.5 or something like that, that means you messed up. They need to be a whole number integer. So it's going to be 0, 1, 2, 3, 4. You can't get any halves or stuff. So if you do get something like that is a half, that's a probably pretty big hint that you've accidentally forgotten one of these extra rules here, that halogens count as hydrogens and nitrogens will count as like a carbon. So we'll go and stop the video there, and then in class we'll go through and do a bunch of practice on turning that number into an actual structure.